It is a project about the Richardson extrapolation applied for partial differential equations, PDEs. You learned the Richardson extrapolation in section 4.2. It is a numerical technique that can produce a numerical solution of higher order equation when numerical solutions are available on two different measures. A mesh n is defined one. By applying extrapolation recursively, the method becomes a sequence acceleration method that can improve the rate of convergence of a sequence. We can apply this technique for the numerical solution of PDEs. However, we have an issue. The Richardson extrapolation can compute the solution of higher order equation on the coarse mesh only. Let's look at this figure. Okay. For simplicity, we consider PDEs in 1D, and this is a domain. This is a mesh, and its refinement here. Same grid point n. Now, by using red pen, let's try to see some extra grid points. Okay. Assume two numerical solutions are available on this mesh and is defined one. Then the extrapolation is possible only on this grid point on the coarse mesh. And for those red points, there are no value available, so that you cannot get the value over there. But the Richardson extrapolation, the solution is on this quality, but available points are on this coarse mesh. So to get the whole values, we need an interpolation algorithm. There are mainly three mathematical interpolation techniques. The first one is completed Richardson extrapolation in 1993. That is a kind of oldest one. And later on, operator-based iterative interpolation and multiple coarse grid extrapolation. And later on, one of these authors, Dai and Lin, in 2018, they published a paper and saying that compared these techniques, and they concluded here the CR, the completed Richardson extrapolation, is the most simple, effective, and popular. The method is based on a simple assumption that the correction term from the low order to the high order is smooth over the whole domain. If we try to say more precisely, we can say this. The correction term is assumed to be continuous and local linear. So in the method, the correction term is interpolated by a linear interpolation method over the phi mesh, and then the interpolated correction term is added to the phi mesh solution to get a higher order solution. In many cases, the simpler, the better. So you can get very simple algorithm, effective, but then usually your result will have a long life. In a complicated one, it's not so effective in most cases. And the extrapolated solutions often show a desired order of accuracy when they compared with each other. However, their error can be larger than that of the numerical solution obtained using the original high-order scheme. Okay, I'll explain this one. For example, we consider one more finer mesh. Then we have 3 meshes. Then we can get 4th order by using this one, and 4th order again by using these 2 meshes. Then if we try to compare after getting errors, this convergence, then you can see 4th order. So from extrapolated solutions, you can get desired accuracy. However, the overall accuracy of the solution is not really same level of that mesh. So that sometimes altogether simultaneously degraded, and then they are showing the desired order of accuracy. But that's not really good one. But anyway, it's quite often showing the desired order of accuracy. However, overall accuracy is not really good. Here, we have a question. Can we get higher order solutions on finer meshes better than the CR method? In comparison, CR is the best one among these 3. Now we try to get better solution than this method. For simplicity, we'll focus on 1D boundary value problems. Okay. Here we have the model problem. We consider this simple, the differential equation minus u second derivative as a right side f pi squared sine pi x, and from 0 to 1, at left edge point the value is 0, and right edge point the value is 2. So it is a sort of a simplest equation. For this differential equation, we have exact solution. U of x is sine pi x plus 2x. For this one, now we try to get partition from 0 to 1 into n equal subintervals. So h, the grid size is 1 over n, and then xr is I times h. Of course, I is from 0 to n, positive integer. Now, UH is the solution, the exact solution in collecting the values at each xi. Now, to get the numerical solution, we try to use, for example, numerical technique for second derivative. You learned this one for second derivative minus u double prime. That can be written in this formula, and these are error terms, and right hand side fi. So at xi, we have this one, and of course when we try to get approximate solution, we'll ignore this portion. So we'll get this algebraic system is not exactly the same as u, but that is an approximation of VUH, right? So after solving this algebraic system, we'll get VH which is an approximation of UH, right? Okay, let's see this remark. In the model problem, we assume we have three different solutions on in fact, three different meshes. And VH, final one, and one more final one. So we have three different levels here, here, and here. Now, once we apply Richardson extrapolation, then solutions of fourth order accuracy. Now, these are second order. So the fourth order accuracy will be obtained through this Richardson and this Richardson extrapolation. So that this extrapolated solution can be obtained on the meshes of grid size H and H of 2. And only this level, but the quality of these values are over there. Quality of this one is on this level. Right? These are fourth order, and we can apply one more time Richardson extrapolation to get sixth order. So by using these two solutions, we can get on this level sixth order solution. But the available values are only on the closest mesh, and that one of grid size H, right? And by applying interpolation method, we can get higher order solutions on final meshes, so that rather than only getting available values on coarser meshes, by using interpolation, we can get the solutions on final meshes over there. Here we have completed the Richardson extrapolation algorithm. We define omega h. Here we define omega h as the set of all grid points. Of course, uniform partition, and we can get grid points, and this is set of the all grid points. Okay, we solve two different second order problems, so we get second order numerical solutions for grid size H and H over 2 or mesh, and its refinement. So after solving this algebraic system, we can get VH and VH over 2. Of course, this is a better solution. Now, by using Richardson extrapolation, we can get a fourth order solution. You already know that, but only is available only on the cos mesh. So the omega h is the cos mesh, and omega h over 2 is the phi mesh. And the available value is only on the cos mesh. So the restriction on the cos mesh, and along with that, you can get this quantity divided by the 1 over 3 divided by 3, and you can get the fourth order solution only on the cos mesh. Now we define the correction term C is now, that will be the fourth order Richardson extrapolated solution. This fourth order one minus the second order one on the fine grid phi mesh is defined to be the correction term. But for the correction term, the available values are on the cos mesh. So the C restricted on the cos mesh will be the definition, restricted on the cos mesh. Okay. Then that is Okay, that's one. But this one, we use this identity put over there. Then now there is a 4, and here now 1/3. So the eventually it is the same as 4/3 of this amount, and minus that one. So the remainder part is 1/3. So by using this identity, we can reach at this term. So 1/3 of, now second order solutions, final one minus cos 1. Okay. Now for this correction term, we apply simple linear interpolation, assuming that now ci minus 1 and ci plus 1 are available. We can get a simple linear interpolation by averaging this quantity to get the midpoint value. Once it is interpolated, then now we can add this interpolated correction term to the second order solution on the fine mesh to get a fourth order solution on the fine mesh. That's the algorithm with the CR method. It can be easily applied for boundary value problems on 2D or 3D. The method involves the simple linear interpolation. Its recursive application may not work to get, for example, the sixth order solutions. You may apply some higher order interpolation method to get more accurate solutions. For the project, a model code is given on from page 477. We'll see it. Okay, here the challenge is, and we have to get solutions of a sixth order accuracy on final meshes by applying high order interpolation technique. So let's consider a specific strategy for a high order interpolation. That is called the method of modified equations. And earlier, that equation, P.1.2, which is this one. From this one, we reorganize and we solve this equation for ui. Okay. Then we reach at this equation. Here, K2 is a fourth derivative of the solution divided by 12, and K4 is this one. Now, we are trying to use that one. The original problem is minus u double prime is f. So we try to make two more derivative and multiply minus 1. Then we reach at this one. So we are using this equation. So that's the reason we call the method of modified equations. Now, u fourth derivative here, that will be replaced by this term. Then, now for this second derivative of f, we can make again here numerical approximation for the second order term, and the error will be order h squared. So that if we consider fi minus k2 h squared, that term, then because of this multiplication, along with this one, of course, modified with that one, and error becomes fourth order. Now, again, we have here h squared, so that now ui is this linear interpolation plus that term and sixth order remainder term. So that if we try to use all this part, then this scheme will be sixth order approximation. So it is a really high order interpolation. And however, this technique is hardly applicable for more general problems, particularly 2D and 3D, and it's not really simple. So in this project, you will not use this technique. There are some specific techniques for given problem. However, some techniques are not really easily generalizable. And this is one example, and we'll not use it in the project. Once you try to apply the CL algorithm for sixth order solutions, then you can do almost the same as in the original CL algorithm. But there are some, okay, let's go back to the CL method. Here, step 1, we try to get in the beginning 2 different level solutions. And if we try to use this technique for sixth order, then these two will be Richardson extrapolations on different mesh. And then we have to get the Richardson extrapolation, and we have to define correction term and then interpolation. So these are almost the same, but now for these two, let's try to get explicit formulas, step 2 and step 3. Okay, for step 2, the sixth order solution of Richardson extrapolation can be obtained with this formula. That is 16 times the fourth order 1 on the finer mesh, and minus and the fourth order solution on the coarse mesh, and divide by 15. That must be sixth order. Now, correction term is similarly defined in this range. From fourth order 1 to sixth order 1, the difference is now the correction term. Again, using this identity for this correction term, we reach this term. And this one will be interpolated in the fourth step, and then this correction term will be added to that one, right? Okay. Here is what to do. Number 1, and try to find 4 different solutions on different meshes. Start with H is 1 over 10. So number of grid points from 0 to 1 is 10, and the final one is 20, and again 40 and 80. Apply the Richardson extrapolation and check the accuracy order as mentioned in remark pair 3, and you can use the definition 5.22 for checking order of convergence. In the model code, this one is done, and this is partially done. We'll see soon. And use algorithm the CR, Richardson extrapolation and linear interpolation. We'll say here RELI. Get fourth order solution on the 3 fine meshes, and so that there are 4 meshes, so that 3 finer meshes, last 3 fine meshes, you can get fourth order solution using linear interpolation. Now apply one more time the CR algorithm to get possibly sixth order solution. And I say here possibly means that it's not really sixth order, but anyway, and you can get sixth order solution on the last two fine meshes from the above fourth order solutions. Are they in a sixth order accuracy? The answer will be no, but we have to check. Yeah? And checking accuracy order is your job. And I did only part of that. And also, for each interpolated solution, Richardson extrapolation and linearly interpolated solution, try to plot error and subtract it from the exact solution. You can find error, and error can be here depicted, and try to see error plots and report those plots. Below is optional for undergraduate students. If you try to do that, if you do nicely, then you'll get an extra credit. Number 4, replace the linear interpolation with a cubic spline interpolation for step 4 of the CR algorithm. Then carry out the step 3. If you are a graduate student, then you have to do this one. Okay. Here is the report information. On the first page, write undergraduate or graduate for your identity. Then add a summary, analysis, and code you implemented, and results, including figures, the plots. For undergraduate students, each step 1, 2, 3, is worth 30 points, and the summary is worth 10 points. For extra credit problem, I'll give you more than 30 points if you do nicely. For graduate students, each step is worth 20 points, and also summary is again worth 20 points. If you use MathTalent, you may start with this code. Now, from now on, we consider a model code. Okay, that is getting algebraic system. Once the interval is given and number of points is given, and also the right-hand side and boundary value, then using them here, A, the metric is open, and B, right-hand side, and this is H for given N. Now this is algebraic system, the metric, that is a right-hand side assignment. And here, this is a specific technique for dealing with the Dirichlet boundary condition. In part 2, in fact, chapter 7 possibly will deal with this technique. Through this function, we'll get anyway A and B for given number of grid points. And this is the simple linear interpolation. Now, P is input and Q is output. First, we measure number of grid points, and that is N0, and that is twice of N0 minus 1, because we are dealing with an algebraic system, and from boundary to boundary, once N is 10, then the number of points will be 11, right? So that in refined one should have here, there must be 21. So that twice of this one minus 1 will be the refined one. And now, after assigning the coarse value to fine one, jumping one, and then here for intermediate values, we try to average the left and right values to get the mid value. That is the simplest interpolation technique. Okay. Now that is the Richardson extrapolation. Okay, here there is initial setting. U is defined as a function of x. That is true. To compare the error, we need to get an array for the true solution. F is the right hand side, and boundary value for the left edge point value is 0. At right edge point, the value is 2. And interval is from 0 to 1, and initial n, number of grid point, number of subinterval is 10, and we have 4 different grid levels. Now, in this portion, and we try to save the result into cell, and U and V. U is exact value, exact solution. V is the computed solution. That is related to the first step. Okay. Now, I is moving from 1 to n grid, which is 4, and n is n0 times 2 to the I minus 1. And then this is the points are made, and U is evaluated and saved into cell ith cell of U. And now, by calling get algebraic system, we can get A and B, and by inverting A, we can get the numerical solution. Okay. Now, in this step, we do Richardson extrapolation. By using in the second order solutions, we can get fourth order one, which is saved into the first column of the cell. And for the second column, we try to get the sixth order. That one is made from now the fourth order solutions, the first column of R, and try to get the second column sixth order. And here you have to have now interpolation for the fourth order one. This is now the correction term. We already know how to get that one. In final one, district on in the better solution, districts on the coarse mesh, minus worst one divided by 3 is correction term that is interpolated and added to the better solution in second order to get Richardson now interpolated the solution. This is fourth order one. Now for sixth order one, you should finish this portion for that second column to get sixth order, possibly sixth order, and then you can check error. Now to show you the performance of this technique, I made this a part of the error computation. Okay, E is error between exact value and second order one. ER is exact value and Richardson extrapolated one. And ERI is now Richardson interpolated value. Let's see the result. Okay. So here, beginning one is second order. Okay. We computed only from 2 to n grid. So and that is 0. So these are meaningless. Anyway, the error here, error here, error here. You can see this is a second order. For Richardson extrapolation itself, we have now error way smaller. But the solution is in this level, but all your available values are one more course level, so that anyway, even though it's half available, the accuracy is really good. Now that one is interpolated, so that on this level we have interpolated value, and every value is available on this level, but through the linear interpolation. So the error becomes larger. It's about 1.5 times larger again. That means that interpolation, linear interpolation, makes larger error. So through applying high order, the better interpolation algorithm, you can get better solution, not introducing extra error. Even though there are some extra error, it must be ignorable. Like this one is larger than, you cannot apply the technique recursively. Of course, when you are using cubic spline, now there's some possibility of applying the Richardson extrapolation to get sixth order solutions. However, it will not be easy. You'll see through this project. I hope you enjoy the project. Thank you.